All right, welcome back. We're going to go through Unit 3, Lesson 8 today, looking at why some cancers appear to run in families. And this is coming right after the Lesson 7 group model that you would make together as a class. So make sure you do that first with me in a small group before moving on to this lesson. We just kind of wrap up in Lesson 7 everything we've been talking about so far. And now we'll start looking at the genetic inheritance of cancer. Okay, starting with learning intention and success criteria, we're figuring out that P53 mutations can be inherited in families or passed down through families. And we can explain why some cancers appear to run in families. Again, that's our lesson question, breaking that down into some smaller things we should know. Why people with Li-Fraumeni syndrome have an increased risk of developing cancer. What pedigrees show us and why we use them. When crossing over occurs, what happens during that process. So what crossing over is, what happens when it occurs, and then how crossing over increases genetic variation. A lot of emphasis is going to be placed on this crossing over and how crossing over increases genetic variation. So make sure we're really focusing on those two when they come up later in the lesson. Okay. So reviewing Lesson 7, I want you to start with your group and discuss just the two prompts here. What did we figure out the last lesson? What did we do in the last lesson? And what do we still need to figure out about who gets cancer and why? So looking back on what we just did in that group model, and you can look at your group model if you want. I'll have it accessible to you. What did we figure out in that lesson? What have we figured out so far in this unit? We're over halfway through now on the downward decline side of the unit. And then what do we still need to figure out? What are we not sure about? And probably should include something about how cancer is inherited, right? We haven't figured out anything about that. We know that's what we're going to look at today. So go ahead and pause the video and discuss that with your group members really quick, and then come back to me. Okay, should be back. Discuss that with our group members, have some ideas about what we figured out last lesson and what we're going to figure out in this lesson. So we have two videos from some cancer survivors. We have Lauren and Lakita. Lauren's 22 years old from Miami, and Lakita is 16 years old, and she's from Kenya. To watch these videos, you just click on the link, and it will take you to YouTube, and you're able. They're not super long video clips. Not going to watch through them with you in this video, but you should pause the video, click on those, watch the YouTube videos discussing these two and their cancer stories, and then come back to me. So pause the video, watch those two on YouTube, and then discuss what you noticed and wondered with your group members, and fill that in on your activity sheet here. So watching those interviews, what do you notice? What do you wonder? How do you feel? Okay, so do that and then come back. Okay, so hopefully we noticed, and maybe we're wondering what Li-Fraumeni syndrome is. That is the disorder that Lakita talked about having, and we probably don't know a lot about that. We know, or hopefully figured, it has something to do with the P53 gene. Okay, and just a quick definition for it if you want to record it, and so you know when it comes up later what Li-Fraumeni syndrome is. It's a disorder that greatly increases the risk of developing several types of cancer, particularly in children and young adults, and it is associated with abnormalities in the tumor suppressor protein P53. So we know that this specific syndrome impacts the P53 gene and prevents that tumor suppression that we've seen P53 kind of do throughout the unit so far. So we're going to look at a pedigree to help us track how something like Li-Fraumeni is passed down generationally from Lakita's grandparents to her parents to her. Okay, so pedigrees can be kind of difficult, kind of hard to conceptualize, to look at. So I'm going to go through it. This is probably, you might need to pause the video a couple of times, might need to slow it down, might need to come back to things. That's okay. This is something that can be a little bit more conceptually difficult to work through, but we're going to work through it together. All right, first thing, anytime you get a pedigree, whether it's on a test, whether it's on an assignment, whether it's just out in the real world, always look for the key. All of them should have a key. just letting you know, because sometimes we'll change what the circles and squares mean. Sometimes we'll change what the shading means, what the coloring means. So always look for the key just to make sure that you know. If there is no key, then just default to this, that squares are male, circles are female. The shading in this representation is the affected person, so the person with a related p53 mutation, and then the slash through the circle or square means that they are no longer living. And then the question mark, as you can see, means they have not been tested for Li-Fraumeni, so we don't know if they have it or not as of right now. And just quickly glancing at it, you can see Lakita's grandfather was unaffected. Her grandmother was affected. Two of her aunts and uncles were affected, and both have died since. Two of her aunts were unsure of, and then her father we do know was affected and is deceased, and then her mother is unaffected, and then she is affected and still living. Okay, so just a quick overview of her family pedigree there. All right, so if each person has 2 copies of chromosome 17, which is the chromosome that has the p53 gene on it, what possible combinations of beads can they have? So we're going to make a model using pipe cleaners and beads of chromosome 17. So if one color represents the allele that corrects mutations and color 2 represents the allele that does not correct mutations, what are the possible allele combinations for someone who has LFS, which is Li-Fraumeni syndrome, but we're just going to call it LFS moving forward. So over on here, there's your definition of Li-Fraumeni. Here is if an individual has 2 copies, what could they have? So I want you to pause and discuss with a group member. Try to figure out if I have those possible color representations, what are my possible combinations? And then I will come back and we will talk about it a little bit more. But I want you to try it on your own with your group members first, and then you can check with me. Okay, so we should have tried it. So we're going to come back here. Okay, so if the first color, whatever color it is, represents the allele that corrects mutations, and the second color represents the one that does not correct mutations. If someone has LFS, then I'm going to assume that they have at least one allele that does not correct the mutation. Okay, that would tell me that they have one allele that is not making functional p53. Therefore, they're going to have this syndrome. So the emphasis is on at least one. They could potentially have 2. So their combination possibilities for me is a color 1 that corrects and a color 2 that does not, or 2 color 2 alleles that do not correct. So those are their options for me. Genetic testing showed that Lakita's grandfather and her mother do not have genes that lead to LFS. That means they only have one version, or only have versions that do correct mutations. What are their possible allele combinations? Well, if to have LFS, I have to have at least one colored 2, then I know my only possible combination is color 1 and color 1. To not have LFS, I have to have all alleles that correct mutations. I cannot have even one allele that is not correcting the mutation. Okay, so possible combinations. If I have LFS, I could have a color 1 and a color 2, or 2 color 2s. If I don't have LFS, then I know I have 2 color 1s. Okay, so we're going to model this pedigree using pipe cleaners and beads, and then complete the follow-up questions in your student activity sheet. All right, so the first color, pink, is going to represent a functional p53 allele or gene, and then green represents a p53 gene that does not work or correct mutations. Okay, so we want to start as we build this model, and you want to build Lakita's grandfather's 2 chromosomes and Lakita's grandmother's 2 chromosomes. Okay, and again, we went through Lakita's grandfather does not have LFS, so what are his allele combinations, right? He's only got one combination. He can have 2 chromosomes that do not have a defective p53 allele, so they're both going to be pink, right? And then her grandmother has 2 possible, and you can pick from those 2 possible. It doesn't matter to me which combination you do. If you want to do she has 2 green, or if you want to do she has a pink and a green, I'm okay with either. That is up to you. And then after that, each parent passes one of their 2 chromosomes to their offspring to make their offspring's chromosomes. So then you're going to go through, and if they get 1 chromosome from the grandfather, 1 from the grandmother, what would this person have? What would this person have? What would this person have? And move down and keep going through that process until you get to Lakita, and then call over me to check, and I will just quickly look at your model and let you know if there's anything missing, if there's anything that needs corrected. And then once it is good, it looks perfect, then you can answer the follow-up questions in your student activity sheet. So you're going to pause the video right now. You're going to go through that process I just described. You're going to build your bead models with your groups, okay? And then when your group has the entire pedigree built, call me over and I will check it off for you or give you any insider assistance that you need. Okay, so you should have your model completed for the entire pedigree, should have been checked off by me. And now we're going to answer these making sense questions. Again, recording answers in the student activity sheet. Okay, so how did you represent chromosome 17 and the p53 gene in Lakita's family? So looking here at the essential key, you can see Lakita's grandfather, like we said, can only have A alleles that are functional. Lakita's grandmother could either have an A allele that's functional and a B allele that's not, or 2 Bs. You kind of get to pick, or you could represent both. I'm okay with either. And then the 2 question mark ants have 2 possibilities. They could both have, or they could have 2 functioning alleles and not have it, or they could have 1 functioning allele and 1 non-functional allele. We know that her aunt and uncle that are affected by LFS have to have at least 1 B allele, and so they got the B allele from her grandmother, and then they got the 1 functional allele from their grandfather. Okay. Same goes for Lakita's father. We know has to have at least 1 non-functional B allele because he has the syndrome, and then has 1 good functioning allele from the grandfather, so 1 of each. And then we know Lakita's mother, just like her grandfather, if you're unaffected, for sure, then you have 2 A alleles that are functional. Okay, and then Lakita, we know the only possible combination, therefore, would be this 1 functional and 1 non-functional. Okay. And then just working through these questions, where did the differences in the versions of the p53 gene come from? So where did they originate in this pedigree? Look up at the very top of the pedigree. Where did this variation, this difference come from originally? Who is passing it on originally based on this pedigree? It could go back further than that, and it probably does. But based on this one, where did it originate? How did Lakita inherit the p53 gene? So where did it come from? And I would kind of like walk through the steps of how it got there. Well, this person had it first. They passed it to this person. That person passed it to this person. Okay. And then how did the p50 gene that Lakita inherited lead to cancer? So how does having a B allele that does not correct mutations lead to cancer? And that's where you're going to pull back on what we talked about leading up to this. All of this leading up to was looking at how cancer cells form and that kind of process of cancer cells forming. Based on that understanding, how do I go from having a non-functional B allele that has a non-functional p53 protein to having something like cancer? Okay. So pause, answer those questions with your group, discuss, come to a consensus. If you're struggling with any of them, then either talk to me in your small group or talk to me when in between group transitions, and I can help you out. Okay, so now we're going to look at Lauren. So that was Lakita. So Lakita has quite a few different cancers, osteosarcoma and MDS. We don't know what kind of cancer Lauren had for sure, though. We know that Lauren's dad had skin cancer and that Lauren had mastectomy, sorry. Okay, so we have another video for Lauren where she's just going to talk a little bit more about her cancer journey and her kind of the cancer experience she had. So you can click on this again. It will take you to YouTube. You can watch that video really quickly. And then you will come back after watching that and discuss these prompts or this prompt with your group. So why do you think people with LFS might get so many different types of cancer? So pause, watch the video of Lauren, answer that question on that previous slide, discuss with your group members, come to a consensus, and then come back to me. Okay, so looking at chromosome 17, it codes for a lot of different genes. Okay, and these are not even all of the genes that this chromosome codes for, right? So every chromosome is going to have tons and tons of genes on it. Obviously, they don't code for just one gene. Otherwise, we'd either have to have a ton of chromosomes or we could only make a couple proteins, which would not be functional for us. So these are just the genes associated with developing cancer. So these aren't even all of the genes on this chromosome. There's many more. These are just the ones we've identified that are associated with cancer risk. Okay, so you can see the P53 gene here that we just looked at, and then the BRCA1 that is associated with breast cancer. So those are the two that we're going to focus on, but understand that even when we just look at two, that's not giving us a whole picture. There is many, many genes on this chromosome associated with cancer. Okay, so we're now going to look at a 2-gene pedigree because the 1-gene pedigree just wasn't fun enough. So we've got to add another gene on there. And this is getting us closer to mirroring what the real world looks like. Again, each chromosome has many genes. So this gives us a better image of what gene inheritance and genetic variation actually kind of looks like in the real world rather than just on paper. Okay, so we have P53 again is going to be represented by these A or Bs. Remember, A means I have a functional P53 gene. B means I have one that is not functional, that's not correcting mutations. And then we're going to look at the BRCA1 gene for breast cancer. And for this one, looking at it, we don't know if C is functional or if D is functional, right? So we're going to kind of try to look at this and figure out which of these genes for BRCA1 is the functional and non-functional, or which one increases cancer risk. We're going to use that using this color key here. So if it is white or lighter green, I have a lower cancer risk. If it is darker green, I have a higher cancer risk. So we're just measuring cancer risk using that color key. Okay, and again, we're going to look at 2 different genes on the 2 chromosomes and see how they're passed down to offspring. So you can see this person has an A and a B allele for P53, a C and a D allele for BRCA1, and they have a pretty high cancer risk. This person has an A and C allele for both of their chromosomes, and they have no cancer risk, or very low, okay? So since I know these 2 A alleles are functional, I already know that A is the functional allele for P53, but now looking at the C's, if I have 2 C's, what does that probably mean for if the C or D is non-functional? Which one, based on just this person here, do you think is the functional version of the BRCA1 gene? Okay. Then as we move down, we can see that this person also only has the A and C alleles, and they also have the white square representing very low to no cancer risk. So again, using that, which do you think, C or D, is the correct or functional BRCA1 gene? Okay, now we move over here. You can see 4. They have a B allele for P53, which I know is not functioning. And then the 2 C alleles, which right now we probably have a good idea of what if the C is the good or bad allele for BRCA1. And you can see that they've got a light green, so they have less cancer risk than this person. Okay, and then finishing with person 5, they have 2 A alleles, so we know both of their P53s are working, and then they have a D and C allele, so now they have a little bit darker green shaded, so they have some cancer risk, not as high as this person again, but still some cancer risk existing. And then comparing like this person, because they have these 2 the same as that person, the only thing that's different here is D and C rather than C and C, and they have an increased cancer risk. What does that tell you about which chromosome is functional or not in the BRCA1 genes? Okay, so pause and discuss with group members using those helpful tips I just tried to give you to answer these questions here on our 2 pedigrees. So which 2 genes does the pedigree model for each gene? What are the possible genotypes? What level of cancer is associated, and which allele is associated with higher risk? So try to fill this in, this table here, with your group members right now. And then I'm going to walk you through it a little bit more step by step. But for now, I want you to just go through that with your group and try to answer that and then come back. Okay. So we should have tried to answer this. I do have a key because I know that this can be confusing, and we're just going to kind of walk through this step by step. Okay, so we know the first A and B. We're going to start with that. We know that the A and B alleles are the p53 gene, or representing the p53 gene. We know the possible genotypes, right? I can have an A and a B, or BA. It doesn't matter. Either way, I have AB are my two possible, right, alleles. I could have that. I could also have two A alleles, or I could have two B alleles. We see all of those combinations represented here. You have an A and a B here. You have an A and an A. Okay. You also have BA, like BAAB, they're the same, or AA. Okay. We do not have BB represented though, but that is a possibility, right? I could have two B alleles and no A alleles. So we know that that is a possibility as well. It's not represented, but we remember, looking back, that that is something that is possible. For BRCA1, same thing. We could have CD or DC, same thing. Or you could have two CC alleles. We see both of those represented here. See, you have CD, DC, CC. What we don't see again is any DD alleles, but we also, again, we know that that is possible. That is a combination that can occur. It's just not represented in our pedigree. What level of cancer risk is associated with each genotype? So for AB, we can see it as high when it is paired with CD, right? So going back, AB and CD gives me high cancer risk. That's the only time I see AB and CD together. Okay, we know it is medium when it's with CC. So again, I have AB and CC here, and I had a medium cancer risk. Okay, so not very high, but not none. AA, I have low to no cancer risk. Again, anytime you saw AA by itself, I had no cancer risk or very low. Okay. And then BB, no information provided because it's not on our pedigree, but we're going to assume we know that that means the p53 is not functioning, so it's probably high or medium, I would say at the lowest. Okay, and then BRCA1 follows a very similar trend. CD is high when it's paired with AB again, medium when it's paired with AA, low when I have two functioning C alleles, and then with DD I have no information, but it's probably going to be high because I know from this that the D allele is the non-functional version. So which allele is associated with higher cancer risk? How do you know? We know that B is already, because when A was by itself, there was no cancer risk or very low. But when B was with A, we saw that cancer risk increase. And then the same trend was true for BRCA1 with the D allele, because when C was by itself, there was low cancer risk or none. But when D was with C, we saw that that cancer risk increased. Okay. So how did the p53 and BRCA1 alleles move from parents to offspring? If mutations explain what we observed in the two-gene pedigree where they have occurred, how can we use our pipe cleaner bead model to help us answer these questions? So this is going to maybe throw you through a little bit of a loop. So when we look at the p53 and BRCA1 genes on this pedigree, we're saying how did they move from parent to offspring? So we know each offspring gets one chromosome. Okay, so for this, they must have gotten this one here and this one here, or vice versa. It could be this one there, this one there. For this offspring, so offspring number 2 or person number 4, however you want to represent it, they got the B allele. The only place they could have gotten it is from person 1 here, but the B was never paired with C. Right? I never had a B paired with a C. So how did I get a B and a C here is kind of our question. How is that possible? And then the A and C could have come from either place. So we know that the B and C probably, or like had to come from the dad, but how did we get a B and a C together? And then a similar truth here, the A and C probably came from the mom. The A and D had to come from here, but how did I get an A and D chromosome when there wasn't one in the offspring? So it does present a problem for us, and we're just going to brainstorm how that could be possible. So a mutation could be one explanation of how that's possible, but where would that mutation occur? So like, if I had a mutation occur that would lead to this mutation, where do you think it would occur? Okay. And this is just like brainstorming, right? We don't know the answers, and that's okay right now. So just brainstorm. How do you think that mutation would have occurred, and where do you think it would have occurred in the process? And then how can we use pipe cleaner or bead model to help us answer these questions? So could we use our model that we did before and add another gene to it, and then go through the pedigree like we did before, and maybe see if we can figure out how this would be possible using that? And maybe we'll see using that how we can have this chromosome that wasn't there before and is there now. Okay, so how could we use that model to maybe help assist us visualize this better? So pause and discuss that with your group, come up with some answers. Again, these are just beginning ideas. We're going to, figure out these things together right now. So we might not have the answers yet, and that's okay. Okay, so we are going to model it using our pipe cleaners and our beads. Okay, so you are going to use light pink for the P53 that corrects mutations, or the A allele. You're going to use green for the P53 that does not correct mutations, or the B allele. You're going to use dark pink for the C allele, that means low breast cancer risk. And you're going to use purple for the D allele, that means high breast cancer risk. And we're going to start, and we're going to build the two parents' chromosomes. So 2 for dad, 2 for mom, so 4 chromosomes, right? And then we're going to have them separate and move and form our 3 offspring, okay? Offspring 1, offspring 2, offspring 3. And then as you're going through this, you're thinking, how is this combination here and this combination here for person 4 and 5 possible? How could that have occurred? And as you're kind of taking the dad's chromosomes, that's who we want to focus on, and we're moving them away, what is something possible that could have occurred just looking at it that would have allowed me to have one offspring get a B and C, and one offspring get an A and D, So what is one possibility that could have occurred in this process that would have led to what we're seeing here? Okay, so pause, redo that model, have me come over and check it, have me come over and help you. I can provide you some more insight in your small groups if you need it as you go through. Once you have that model complete and you think you have an understanding of how we get that combination of alleles in the offspring, then let me know and I'll check it, make sure everything's good, and then we can move on. So pause, revise that group model, discuss those questions, and then talk to me. Okay, to help us, and if you still could not figure out how that was even possible, then I'm just going to refer you to this reading. So what we need to do right now, even if you're like, yeah, I've got this figured out, I know that it's this, and we've talked about it, and I've said, yeah, you're right, you're on the right track. Or you have absolutely no idea, and you're like, Mr. Nichols, I hate your class, I'm never coming back. Then we're going to, either way, come here and read about passing on alleles. So we click on the link here, and it's going to take us to this reading. It's still super short, just barely over a page. And it's going to talk about how alleles like P53 and BRCA1 are passed on. It's going to talk about a new process similar to mitosis that we call meiosis. It's going to show how sex chromosomes end up with different numbers of chromosomes. It's going to finally talk about crossing over here. You can see bolded. That's very important. That was one of our success criteria, was knowing what crossing over is. And then it's going to go more in depth about how crossing over leads to genetic variation and things like that. So make sure we read that right now. Pause this. You can read with group members. You can read alone and then talk with your group members. You can popcorn read at your group. You can read with me in our small group. I'll read it out loud. However you want to do, just make sure we go through that reading. Okay, so now using the reading and the model, you can go back and revise your model now. You should have a very good idea of how we can model what was occurring with the beads. I hope maybe it's kind of like if you weren't figuring it out, it was like an aha moment of oh crap, it really was that simple, of course. So you can go back and revise that now. And then once that model is all set to go and been checked off by me and drawn in or represented in your notebook, then we're good to do this building understandings questions. Okay, so we're going to work through these in your group. I'm going to give you guys some prompts to help you, and then you'll check them off with me in our small group discussions. So how does your model help explain how alleles were passed down in our pedigree? So after the reading, how can you use that model, and how did you use that model to help us show how it's possible to have these different combinations of alleles that we hadn't seen before? What effect does, and this is a hint for the last question, what effect does crossing over have on genes and alleles on chromosomes? So after reading about crossing over and modeling that using your pipe cleaner, how is that process, if it's kind of like constantly occurring, right? It can occur randomly within my cell at any time. How is that going to have an effect on genes and alleles on chromosomes? And how is that going to increase genetic variation, right? If before we talked about crossing over, there's very few possible combinations, right? It can either have my A and B, or my C and D, or my CC, or my DC, right? And I can only pass on the combinations that I already have. But after crossing over, now there's a lot more different combinations that I could have and pass to my offspring. Where did the version of genes that increase the likelihood of P53B and BRCA1D come from? So where did, in Lauren's case, that pedigree we just looked at, where did those genes actually come from? So how was it possible for an offspring to have the B and the D allele when neither of the parents had that? Okay. And then how could crossing over help explain Lauren's situation? So again, if we're saying that this pedigree represents Lauren and her family, where we're saying like her dad had a mutation on one chromosome for P53 and one for BRCA1, how would it have been possible for like Lauren to have all of these things, right? How would this and for everyone, like even if your parents maybe don't have one of these or only had one gene, how does that impact your ability now to maybe potentially develop cancer? And how does that increase cancer risk for everyone in general too? Is since we can kind of reshuffle alleles, now it's a little bit more complicated when we look at the gene inheritance for things like cancer and other genetic disorders. So how can crossing over help explain things like Lauren's situation? Pause and discuss those with your group members, come to a consensus, answer those questions on your activity sheet, and then come back. All right, and then wrapping up the lesson, the last thing we have is our progress tracker, going back and answering these success criteria questions in your progress tracker, and then showing that progress tracker to me for your mastery check. And then looking forward, we're going to look at how the environment increases cancer risk. So next lesson, we're going to focus on the environment, and we're wrapping up and getting close to the end here. So if you guys have any questions, if you need any assistance with this lesson or any other lesson, let me know, and have a great day.